Welcome to this special explainer. Okay, picture this. You're sitting at your kitchen table and it is a total mess. Right in front of you, you've got a spilled glass of juice, a cup of milk, sugar scattered everywhere, and for some reason, a glass of muddy water from outside. It looks like absolute chaos, right? Well, what if I told you that we can actually bring perfect, scientific order to all of this chaos? Yep. Today, we're going to take literally everything around us and organize it into a beautifully structured, completely logical system. Let's get started. Okay, let's dive into this. Imagine a mother sending someone to the store early in the morning, specifically asking for pure milk, right from the source, before any water gets mixed in. To us in everyday life, that's pure. But in chemistry, the word pure means something entirely different. Actually, by the strict laws of science, that fresh, unadulterated milk is totally impure. To understand why, we've got to map out the physical world. So here's how we're going to methodically break this down and conquer it. 1. What is matter? 2. Pure substances. 3. Metals, nonmetals, and metalloids. 4. Impure substances, also known as mixtures. 5. Understanding alloys. And finally, 6. Solutions and concentration. To keep things moving, we've broken this down into 5 quick sections to act as our roadmap. What is a mixture? Types of mixtures, concentration, and then we'll wrap up with separation techniques, parts 1 and 2. All right, kicking things off with our first branch, section 1. What is matter? At its absolute core, matter is literally anything that occupies space and has mass. Think about it like a really skinny kid going on a road trip with his friends. His friends might say, oh, just squeeze him in the back, he takes up 0 room. But the truth is, no matter how tiny or skinny he is, he still takes up some space, and he definitely still has some mass. So, boom, he is matter. Basically, everything around us that has even a tiny fraction of mass and occupies any space at all fits right into this classification tree. Moving down the tree to section 2, pure substances. So, pure substances are divided into 2 main camps, elements and compounds. Elements are essentially the singles of the chemistry world. They're just one type of atom flying solo. Think of an isolated chunk of iron or pure gold. It is just one thing. Compounds, on the other hand, are 2 or more elements chemically combined together. For example, if you take the element sodium and chemically bond it with the element chlorine, they lose their individual identities and become something totally new, salt. And this brilliantly illustrates why compounds are considered truly pure. Pure compounds have these strict, fixed, unwavering proportions. Take water. A single water molecule will always have a 1:8 mass ratio of hydrogen to oxygen, always. If you change that ratio even slightly, well, you don't have water anymore. You've got something completely different. It's this perfectly fixed recipe that makes a compound a pure substance. Next up, section 3, metals, nonmetals, and metalloids. Let's rapidly break these elements down, starting with metals. Metals have very specific properties. They are lustrous, which just means shiny. They're malleable, so think of how a mother's gold jewelry can be beaten and shaped into these thin, beautiful designs without breaking. They're ductile, meaning they can be stretched out into long wires, kind of like pulling apart sticky bubblegum. They're sonorous, which means they give off a ringing sound when you strike them. And of course, they are fantastic conductors of heat and electricity. Now flip the script, because nonmetals are basically the exact opposite. They're dull, they're brittle, so they shatter instead of bending. They are terrible conductors, and if you hit them, you definitely won't hear any nice ringing sound. They mostly just sit there quietly. But, science loves to throw us a curveball, so we have to highlight the massive exceptions here. Metals are pretty much all solids, right? Well, except for mercury, which is technically a metal but just sits there as a liquid at room temperature. And nonmetals are supposed to be terrible conductors? Well, graphite, the black stuff inside your pencil, is a nonmetal, yet it perfectly conducts electricity. And then we have the third category, metalloids. Picture a typical classroom. You've got the high-achieving toppers sitting on one side and the loud backbenchers hanging out on the other. Metalloids are like those students sitting right in the middle trying to hang out with both groups. They share intermediate properties of both metals and nonmetals. They're just caught right in the middle. All right, jumping over to the other main branch in section 4, impure substances, otherwise known as mixtures. So the crucial point is understanding the fundamental difference between a compound and a mixture. Remember, a compound is chemically combined, creates totally new properties, and requires a strict fixed ratio. A mixture, it's just physically mixed together. You can mix stuff in literally any variable proportion you want, and importantly, the items in a mixture keep their old properties. If you mix salt and water, the water is still wet and the salt still tastes salty. Now, mixtures split into two camps. Homogeneous mixtures are completely and uniformly mixed. Think of sugar completely dissolved in water. You literally cannot tell the sugar and water apart anymore. Heterogeneous mixtures are the exact opposite. They do not mix uniformly. Think back to that glass of muddy water on our kitchen table. If you let it sit for a bit, it separates out into distinct, totally visible layers. And here is where we bust the ultimate myth from the beginning of our explainer. Milk looks homogeneous to the naked eye, right? It looks like one uniform white liquid. But if you put that milk under a microscope, you'll clearly see separated particles of fat and liquid just floating around. Because it has those separate, distinct parts at a microscopic level, our so-called pure milk is actually an impure, heterogeneous mixture. Mind-blowing, right? Moving on to a tricky one, Section 5, Understanding Alloys. Seriously, if you can grasp this, you are truly succeeding. Okay, we need to talk about alloys, like steel or brass. An alloy is a combination of two or more metals. Now, you might be thinking, wait, combining two elements makes a pure compound, right? Actually, no. Alloys are mixtures. Why? Well, because you can mix them in variable proportions. You don't need a strict chemical recipe. Plus, they retain the properties of their base metals. They don't form a completely new chemical identity, they just sort of blend their strengths, resulting in incredibly high melting points. That's exactly why we use them for things like heating coils and cooking pots. And our final stop, Section 6, Solutions and Concentration. Scientifically, homogeneous mixtures are known as solutions, and a solution is made of just two parts. There's a funny little analogy for this. Think of making the juice of love, or just a perfect glass of sweet lemonade. The sweet sugar you're dissolving, that's the solute. The water doing the dissolving, that's the solvent. Solute plus solvent equals your solution. Simple as that. When working with solutions, we often need to measure their concentration. Now, don't let the math here overwhelm you. It's actually super simple, and I want you to drop a comment right now saying I can do it just to lock that motivation in. Look, for a mass percentage, you just put the mass of the solute over the total mass of the solution and multiply by 100. If you need volume, it's the volume of the solute over the total volume of the solution times 100. And you can even mix them. Mass of solute over the volume of the solution times 100. Just follow this basic logic step by step, and you've absolutely got it. Now, what's really interesting about this slide is how easily we can manipulate these mixtures. If you add more of the solute, like aggressively stirring more and more sugary powder into a drink, the liquid gets darker, sweeter, and highly concentrated. But if you pour in more solvent, like just adding a big splash of plain water, you do the exact opposite. You dilute the solution, drastically lowering its concentration. As we wrap up this massive breakdown of matter, I want to share a little philosophical thought to anchor our scientific journey back to the human experience. There's a saying, what is yours will stay with you, the rest is an illusion. Think about it. The hard-earned knowledge you've just gained today about classifying literally everything in the universe, that is yours. It's locked right there in your brain and absolutely nobody can take it away from you. So, I want to leave you with one final provocative challenge. Look at the object nearest to you right now. Could be a pen, a cup of coffee, your phone case. Look closely at it. Armed with your brand new classification superpower, ask yourself, is it a pure substance or is it a mixture? And if it's a mixture, is it homogeneous or heterogeneous? Keep analyzing your world and stay curious. Jump right into this explainer. Today, we're going to completely dismantle the chemistry of everyday life. We'll be looking at everything from your kitchen counter right up to massive industrial laboratories. We usually look at the stuff around us and assume, oh, that's just one simple substance. But the reality, we are constantly surrounded by these incredibly complex, perfectly balanced chemical mixtures just waiting to be explored. Let's get into it. All right, Section 1. What is a mixture? We're going to start by challenging your entire idea of purity. So you might look at a glass of milk or a shiny gold ring and think, wow, that's a perfectly pure substance. But scientifically speaking, no way. That 22-karat gold jewelry you buy actually has to have a specific amount of copper mixed into it, just to make it durable enough to wear. And the air we're breathing right now, it isn't just oxygen. It's this massive cocktail of nitrogen, carbon dioxide, and yeah, pollutants. Milk is actually a super complex mixture of water, lactose, helpful bacteria, proteins and fats. Even that glass of lemonade you make at home, where, everyone wants a slightly different amount of sugar or salt, is literally the perfect example of how a mixture doesn't have a fixed, identical composition every single time. Okay, moving on to section 2, types of mixtures, where we categorize exactly how these blends behave. Now, there's a really crucial difference between the two main types of mixtures out there. On one hand, we have perfectly uniform, homogeneous mixtures. Think of a thoroughly stirred glass of lemonade. The very first sip and the absolute last sip, they taste exactly the same because the ingredients are distributed uniformly. But then, on the other hand, you have heterogeneous mixtures. Imagine mixing chalk powder into a glass of water. Those ingredients just stubbornly refuse to blend evenly. If you dip a spoon in at the top, you're getting mostly water, but scoop from the bottom, you're pulling up a big heap of chalk. Whenever you do manage to get one of those perfect, uniform, homogeneous mixtures, science calls it a solution. And a solution always comes in two parts. You have a smaller substance, that's the solute, like your sugar, which dissolves into a much larger substance called the solvent, like your water. It's basically like the solvent entirely swallows up the solvent until they look like one single entity. Which brings us to section 3, concentration and solubility. Let's look at the math and the physical mechanics behind how much solute we can actually force into these solvents. Now, the really important takeaway here is that concentration isn't just some abstract concept for a chemistry lab, it literally dictates your everyday life. For instance, when we measure mass by volume, we're figuring out the exact strength of a life-saving medical IV drip. Or when we measure volume by volume, mixing two liquids together, we get things like that household vinegar you splash on your noodles, which, by the way, is really just 5 milliliters of acetic acid hiding inside 95 milliliters of water. So pause for a second. Imagine a glass of water sitting right in front of you. What actually happens if you simply refuse to stop adding spoonful after spoonful of sugar? Does it just keep dissolving forever? Well, eventually, the water basically just throws its hands up in defeat. It hits an absolute ceiling, its maximum solubility for that specific room temperature. The sugar will just start piling up at the bottom of your glass. Once a solvent absolutely refuses to dissolve even one more single grain of solute, boom, you've created what chemists call a saturated solution. All right, section 4, separation part 1. Now that we've built these mixtures up, let's see how science untangles them. What's super interesting here is how this mimics the traditional confectioner's approach to making sweets. If you want to force way more sugar into water, what do? You heat it up to make a syrup. But what happens when that superheated, totally saturated syrup goes into the fridge to cool down? The cold environment literally forces the sugar to undissolve. It separates back out into these visible, beautiful, completely pure solid crystals. This whole process, crystallization, is an incredibly effective way to purify solid substances. But what if you're trying to separate two liquids that have perfectly blended together? Well, you need a boiling point difference of at least 25 degrees Celsius. That right there is the magic number to easily and safely pull them apart. And that brings us to simple distillation. Say you've got acetone mixed in with water. Acetone boils at roughly 60 degrees Celsius, while water boils at 100. So, if you carefully heat up that mixture, the acetone turns into a hot vapor first. Then, we guide that hot vapor through a special glass tube that is constantly cooled by cold water on the outside. That sudden temperature drop, it forces the vapor to condense right back into a liquid, dripping into a totally separate container as pure acetone, all while leaving the water behind. It is honestly a beautifully elegant physical trap. Finally, section 5, separation part 2. Let's scale things up to an industrial level. When the boiling point difference between two liquids is extremely tight, like less than that 25 degrees we just mentioned, we have to scale up to something called fractional distillation. This is exactly what's happening at massive petroleum refineries. They take a thick, gooey mixture like raw crude oil and carefully heat it to extract distinct layers. This one single process gives us everything from the heavy diesel powering massive transport trucks all the way to the petroleum jelly you rub on dry skin in the winter. Now, let's talk about colors. If you were to take a black ink spot on a piece of paper and dip just the bottom of that paper in water, you'd witness paper chromatography in action. As the water creeps up the paper, it grabs onto the ink. And because that little black spot is actually a hidden mixture of lots of different colored dyes, each with a slightly different solubility, the colors literally separate out as they race up the paper at different speeds. But look like one solid black dot suddenly blooms into this rainbow of blues, yellows, and reds.
Now, for liquids that naturally hate each other and flat out refuse to mix, we call these immiscible liquids. Like oil and water, the separation process is a total breeze. We just pour them into a separating funnel and let gravity do all the heavy lifting. Because water is denser, it sinks right to the bottom. Then we just open a little valve called a stopcock, drain out the heavy water, and quickly snap it shut right before the lighter oil can escape.
In wrapping up our techniques, we have sublimation. This is an almost magical process where a solid completely bypasses the liquid phase and transforms directly into a gas. Think about camphor, used in traditional ceremonies, or those solid blocks of bathroom air freshener. Over time, they don't melt into a gross puddle, they just shrink and vanish straight into the air. If you capture that vapor and cool it down, you can turn it right back into a pure solid, completely separated from any non-sublimating impurities. So, I want to leave you with this thought. We've just explored the hidden complexities of the things you touch, taste, and use every single day. The next time you hold a piece of jewelry or stir some sugar into your tea, what other invisible mixtures do you think are hiding in plain sight, just waiting to be decoded? Thanks for tuning into this explainer, and keep questioning the world around you.